Hello everybody, so this is the course of 3DF of Tuesday the 2nd of June, and we are doing today all these exercises about magnetism, okay? The first exercise states another rule than the right-hand rule, which you might find easier. And this rule tells you that if you turn in the direction at which I approaches the vector B, then the direction of movement of the corkscrew indicates the direction of the force. So I recalled here the basic right-hand rule. If you have the magnetic field in the direction of your middle finger, if you have the current in the direction of your index, then you will have the force in the direction of your thumb. Okay, these forces are always perpendicular. So here, if I have the magnetic field which is going down, the current which is going to the left, then my force is going to come towards me. Okay, now with this corkscrew rule, corkscrew means tire-bouchon, c'est la règle du tire-bouchon. What happens? Okay, we have a magnetic field which is going down. We have a current which is going to the left. Okay, so now what do? Read the sentence. If you rotate a corkscrew in the direction that the vector I approaches the vector B, if you go from the vector I to the vector B, you turn in this way. Okay. And if you turn a corkscrew in this way, it's going to do what? It's going to come up, right? Because you are unscrewing it actually. So the force is going to come up towards you, right? Now, if you have the magnetic field which is coming down here and the current which is going to the right, well, in that case, when you go from the vector I to the vector B, you turn in the direction in which you screw, and so this force is now going down, and this is all consistent with the right-hand rule. Okay, are you with me? Do you agree? Do you agree?
Yes, of course.
Of course. Okay, express a Tesla in the units of the international MKSA system. So the MKSA system is meters for distances, Kelvin for temperatures, seconds for time, and amps for the electric current. Okay, so let's try, but how could we do that? How could we do this? If I ask you that in a test, you will do what? You will do what? Well, you will take a formula which expresses the magnetic field as a function of other quantities, and you will see what you get. For instance, we could use that formula or this formula. Okay, let's say we will use this formula. Okay, B is equal to mu over 2 pi times I over D. Okay, B is equal to mu over 2 pi times I over D. Of course, mu is a constant, so we need to know the units of that constant. So I gave you the units. It's volts times seconds divided by amps times meters. Okay, you see it here, the unit. Okay, this is let me take a different color. This is, what did I say? I don't even know it. It's a shame. Volts times seconds over amps times meters for the mu. Okay, 2 pi has no units, and I is in amps and D is in meters, right? So now we can say, okay, this is volts times seconds divided by amps times meters, times amps divided by meters. Do we agree with that? Okay. So what do you do now? You have amps up and down, so they cancel. You have meters, they become squared. So this gives you volts times seconds over meter square. Okay? I said something very stupid before. Maybe it's because I'm not feeling well. This is, of course, not kelvins. This is kilograms. Sorry. I'm a bit out of my mind because I don't feel so well. Okay? So volts times seconds over meter square. Okay, let's not spend 3 hours on that. Now let's go to the third exercise. The third exercise tells you look in the CRM table for some values of magnetic fields. Well, let's look. So how do we look in the CRM table? We take the index at the end, okay, and we look for champ magnétique. Okay, so if I look at champ magnétique 144, intensité 177. Let's try with 177 intensities. Okay, well, here you have it. Intensité de quelques champs magnétiques. Okay. Let's start maybe with the magnetic field of the Earth. 3 times 10 to the minus 4, this is all in Teslas. 3 times 10 to the minus 4 Teslas. Okay, just to give you a comparison base. Okay, you see that the magnetic field of the sun, of course, there is also a magnetic field in the sun because there is also matter moving inside the sun. Of course, matter is moving. The sun is a fluid, okay? It's round just because of gravitation. Otherwise, it's a fluid. The sun's magnetic field is about 10 times bigger, okay? And then you can compare to a classic magnet, one of these magnets you can play with. Well, take into account the fact that this table is quite old, okay? I have my table. My table is dated, which date? Which edition do I have? Why don't they put the edition clearly? Okay, 2008. So it's quite recent. But recently, new magnets have arrived on the market, the neodymium magnets. Maybe if you take a modern value for that, it will be a bit higher. Now you see solar flare, tache solaire, I think we say like that, 10 to the minus 1. So these spots we see on the sun are actually due to the magnetic field of the sun being different. Okay, all you have here, the neodymium permanent magnet, these have a field which is much more intense than magnetic stars. And then you have all these things here. You see that the object that has the biggest magnetic field is a neutron star. Of course, it's far from us, so we don't need to be scared of that. 10 to the power 8. Then a superconducting magnet, 40 Tesla. Do you know what superconducting means? Superconductivity is an extremely interesting property of matter. Superconductivity. Conductivity. What is that? It is a phase of matter which happens at very low temperature, in which the electrical resistance becomes zero. Okay? If you take a superconducting wire, you cool it down at minus 270 degrees Celsius, so close to the absolute zero, then this superconducting wire is going to have a resistance which is exactly zero. Okay, we have the possibility to have zero resistance in some materials, And the big advantage with that is that if you have zero resistance, you don't lose any energy in the cables, okay? So that's why we use superconducting cables for applications in which you need a lot of current to pass through something without this something getting warm. And if you have zero resistance, there will be no electrical energy transformed to heat, so it's fine, okay? Plus, you can send as much current as you want without having to fight electrical resistance. So we use this kind of cables for very high-end applications like the accelerators at CERN, for instance, like maybe some big machines like MRI machines. I'm not sure whether they use superconductors or not. Okay, but this is clearly the way to make a very intense electric field, because if you have a magnetic field, because if you have a self which is made out of a superconducting wire, you don't need to worry about resistance. You can have lots of current flowing into that, and you can generate an important magnetic field. Okay, and then you see the other values of the magnetic field. A galaxy has a magnetic field, but it's not very strong. Around a cable, this is interesting for you maybe. If you take a transport line of 765 kilovolts, so this is a very high voltage line, okay, and it carries 4 kiloamps. If you stand at 16 meters, in other words, if you stand at the ground, you have a magnetic field 0.5 times 10 to the minus 4, which is comparable to the magnetic field of Earth. Well, it's 6 times less intense than the magnetic field of Earth, but there is still a magnetic field. Okay, this is why people say we shouldn't live under a high tension line. Actually, what happens with a high tension line? Can you imagine what happens? Okay, imagine here you have a high tension line which is passing over your house. Okay, how is the magnetic field going to look like? Let's assume the current goes in that direction. What would you say? The magnetic field looks like what around that cable? Hello, hello, it's time for you to say something. You remember the shape of the magnetic field around a wire? You remember that? Yeah. Well, yeah, it's a way of saying it, okay? The correct way is to say, okay, if you can draw a circle around the cable, and the magnetic field is going to be at any point tangent to this circle. Okay, it's not moving around, but it's tangent. Okay, so what will happen in your house if I draw it from above? This is your wire, this is your house. Well, you're going to have inside the house a component of the magnetic field which is perpendicular to the wire and which is pushing in that way. Now, of course, if the current is oscillating, if it's an alternative current at a frequency of 50 hertz, which means that one cycle takes 1/50th of a second, then the magnetic field, which is here, is going to change direction, because when the current is going that way, the magnetic field is turning like this, and when the current is going the other way, the magnetic field is turning in the opposite direction. Okay, so if you have a wire over your house with a 50 hertz alternative current, you will have inside your house an alternative magnetic field which changes direction. I mean, it goes from here to there and back 50 times per second. So it changes direction 100 times per second. And we don't know exactly what the effects of that on health are. Certainly, it perturbs the motion of electric charges inside the body. By how much? What's the effect of a prolonged exposition to that? We don't know. What's the effect of a frequency as low as 50 hertz? We don't know exactly. Okay, but I would never buy a house under a high tension line, that's for sure. Okay, and if you have a house and somebody puts a high tension line on top of your house, it's going to lose a lot of value because nobody wants that. Okay, good. Let's do some computations now. In the case of two parallel wires, each traversed by a current of 1 amp of length 1 meter each and distance of 1 meter from each other, what is the intensity of the interaction force between these wires? So you have everything in the course to do that. I let you do it. You have all the formulas in the course. Okay, well, let's look for the formula together. Let me accompany you. Okay, the force between two wires is given by this formula. Mu L I1 I2 divided by 2 pi d. Okay, the force, what did I say? God, is mu L I1 I2 divided by 2 pi times the distance. Okay, this is the case of two wires. These wires are 1 meter long. They are 1 meter apart. Okay, you have a current I1 flowing in one of them, current I2 flowing in the other one, in the other direction. The distance is this. The length is the length of cables. Okay, it's normal that the force increases if the length of the cable increases. It's normal that the force decreases if the distance increases. So this is the right formula. Okay, so now try to compute it. You need the value of mu, of course, and the value of mu. Where did we give it? It's here, 4 pi times 10 to the minus 7. So mu is 4 pi times 10 to the minus 7. Okay? So you can do the computation. Okay? It's 4 pi times 10 to the minus 7 divided by 2 pi times the length. The length is 1 meter. Okay? This is the length of the two cables which are parallel. So this is the part of the cables which is interacting. We have a current I1 of 1 amp. We have a current Y2 of 1 amp. And we have a distance of 1. So it's a very difficult computation. This simplifies, you have a 2 here. So it's 2 times 10 to the minus 7, and the unit, of course, is newtons, because this is a force we are computing. Okay? So you see this force between two cables, it's not extremely strong, but it's something noticeable. Of course, if the cables are closed, then this force becomes high. Okay. C'est bon? Can I pass to the next? Good. Allez, let's do, how many do we have? Yeah, let's finish that today. They are easy, small exercises. What is the direction of this force when the currents are going in the same direction? What is the meaning when the currents go in opposite directions? Aha. So now we have to consider two cases. Okay? One case in which the two currents go in the same direction, and one case in which the two currents go in opposite directions. And how do you think we could do that? You have an idea? We're going to use our right hand. Okay, but how? Hmm? Oh God, you're tired. How could we use the right hand here? Hmm? Okay, let me do it for the case of two wires with the current going in the same direction. By the way, this is the case which is in the course. You see that here it gives you a force which is attractive. Let's try to check that. How do we check it? Well, let's consider one of the cables, like this one, okay? If we want to determine the direction of the force, we need to know the direction of the magnetic field, right? Because the force is given by ILB. Okay, it's given by the product between the current, well, the length of the cable in the direction of the current, and the magnetic field. But the magnetic field which is acting on this wire is the one generated by the other wire. Okay, so this wire, it generates a magnetic field which is turning in some way. And in which way is it turning? Well, we have to use the right-hand rule. And this right-hand rule which tells you in which direction the magnetic field is turning. So here, if you put your thumb in the direction of the current, it shows you that the field is turning in that way. Okay, so we have a magnetic field which is here. Well, let me draw it properly. Here it's coming to the front, here it's going to the left, and here it's going to the back, the magnetic field. Okay, because the magnetic field is turning like this, right? Magnetic field is going to the back. Now, if the magnetic field is going to the back, are you able to tell me in which direction the force is going? Well, the question is in which direction is the force acting here if we have a length of cable going down, I mean a current going down and a magnetic field going inside the page. You have to use your right hand. Okay, you put the middle finger in the direction of the magnetic field. You put your index in the direction of the current, and you have the force in the direction of the thumb, which is to the inside. Okay, so here the force is attractive. And now if you do it for the other cable, what do you think? Is going to be the same? Yeah, it's going to be symmetric. Let's do it. The current goes down, so the magnetic field here is turning also in this direction, okay? And so here it's coming out from the page, right? You see here it's going in, but here it's going out. Now, if the magnetic field is going out, sorry, I will do something very bad to you, and the current is going down, magnetic field is coming up, the current is going down, the force is going to the left, right? So you see that with two parallel cables, the forces are attractive forces, okay? And now, as you expect in that case, of course, there will be repulsive. How does that work? Well, the direction of the magnetic field here is changed. Now you have the current going up, okay? So the magnetic field is turning this way, okay? So I can draw here, and here the magnetic field is coming out of the page, which is exactly the opposite of that, okay? So now with the magnetic field coming out of the page and the current going down, okay, the force is going to be to the outside, right? And now we do the same drawing on the other cable. Here, the current is going down, so the magnetic field is turning like this. So here, sorry, it's going down. No, sorry, it's going up. The current here is going up. Wait, I'm confused now. Here it's going down. Oh yeah, so here we have a magnetic field which is coming up to, okay? And so if it's coming out and the current is going up, it means also that the force is directed to the outside. So if we have two cables with opposite directions of the current, then we have a repulsion between these two cables. Okay? Okay. Okay, here we have the problem of the intensity of the magnetic field 10 centimeters away from a wire, and this wire sees a current of 5 amps go through it. Okay? Well, first of all, what is the direction of this magnetic field? Can you tell me? Right hand rule. Put your thumb in the direction of the current, and your magnetic field is turning like that. Okay? So here, the magnetic field is going to go inside the page. Okay? And now about the intensity, well, I gave you the formula, okay? I gave it to you without too many definitions. It's the same formula we used before, mu over 2 pi times I over d. Okay, so B is equal to mu over 2 pi times I over d, okay? And mu, we saw that it's 4 pi times 10 to the minus 7. So when you divide by 2 pi, you have 2 times 10 to the minus 7 remaining. Then you have the current. We said a current of 5 amps at a distance of 10 centimeters. So you have to divide by 0.1 in meters, of course. Okay. And now how much is all that? 5 divided by 0.1, this is 50. 5 divided by 0.1, this is 50. 50 times 2, this is 100. 100 times 10 to the minus 7, it's 10 to the minus 5 Tesla. Okay? But this is in which substance? This is in which substance that we did this calculation? Can you tell me? In the air, okay? Because we used a value for mu, which is the mu of the air, and the mu inside air has approximately the same value as the mu in vacuum, okay? You see the value 4 pi 10 to the minus 7 is in vacuum, but in air there is a slight difference. But for what concerns us, we can approximate that to the value of the mu in the vacuum, okay? Now we have iron and steel, okay? What do we need to okay, we need to compute in iron and in steel. So in iron, I will write it here, the mu is 2000 times the mu 0, and in steel, the mu is 150 times mu 0, and mu 0 is 4 pi times 10 to the minus 7. Okay? So, question A. In air, it's this value. Now, question B is in soft iron. What happens if you change the value of all this to use the mu of soft iron? Okay? Mu soft iron over 2 pi times I over d. What happens? This multiplies the final result by how much? You see there is a factor 2000 here. Okay? And this factor 2000, you can take it out. It's going to give you 2000 times this value here, times to the 10 to the minus 5 Tesla. Okay? And 2000 times 10 to the minus 5, this is 2 times 10 to the minus 2 Tesla. So you see that if you create a magnetic field inside a substance which is not air, you can make it stronger. Okay, this is why often inside a self, inside a bobine, you have a core of soft iron. Soft iron is very often used to make magnets because it allows you to have a magnetic field which is much bigger than what you would have inside air. Okay? Okay, and now of course the third one, well, there is a factor 150, so B is mu. No, it's not iron, it's steel, sorry. It's steel over 2 pi times I over D, and so this is now 150 times 10 to the minus 5, so it is 1.5 times 10 to the minus 3 Tesla, okay? And all these values are greater than the value in air. Okay? Okay, try to do exercise 7 by yourself. Yeah, this you know. Okay, we assume that we have a current which is perpendicular to this sheet and it leaves it, let's say it comes above, okay? Let's say that we have a current which comes up in that direction. Can you draw me the magnetic field? Yes, you can. And let us just check that. So, what do you think? Allô, allô? Allô, allô? Well, you put your thumb up because the current is coming up and so it's turning that way. Okay? So here, if I want to draw my magnetic field, I can draw like circles around this current, and then I can put arrows which are tangent to the circle in the direction of rotations that I have determined. And the intensity of the magnetic field, which is represented by the length of the vectors, this intensity decreases with distance as 1 over the distance. So if you are a bit further, the magnetic field is a bit smaller, and as you go further, this magnetic field decreases in intensity, but it is always perpendicular. It is always perpendicular to the current and tangent to the circle that you draw around the current. Okay, all these small arrows that I drew, they are the magnetic field. So the magnetic field clearly is all around the cable. There is an infinity of these arrows that you can draw, draw, but we don't draw an infinity. We just draw a few. Okay, and then let's suppose here I have a point. I want to know the direction of the magnetic field. Well, what do? I can trace a line between the center of the cable and the point, and my magnetic field, I know that it's going to be in the direction perpendicular to the axis, to the line which goes from the point to the wire. Okay? Very generally, it's that. With my right hand, I put my thumb in the direction of the current. So now the current is coming up. So I put my right hand like this, and the direction of my fingers tells me how the magnetic field turns. Okay? Good. Haha, does a stationary electron undergo a Lorentz force? Aha. So what do you think about that? Well, first of all, we need to recall the Lorentz force. Okay, so we gave it here. I think it's in this chapter. The Lorentz force, we said it's QV cross B. The Lorentz force, it's Q times the velocity of the electron times B. Okay? Notice that this is a general formula because if the charge is positive, the force is going to be in one direction. And if the charge is negative, the force is going to be in the opposite direction, which is nice. Now that you see that equation, can you answer the first question? Okay, the stationary electron, does it feel a force? Will a stationary electron feel a force? Tell me, yes or no? What does stationary mean? It doesn't move. If it doesn't move, what's its velocity? Zero, okay? If the velocity is zero, what do I get for a force? Zero, okay? So the Lorentz force in that case is 0 newtons, okay? As I told you, magnetic forces act only on moving electric charges. They don't act on electric charges at rest, okay? So indeed, if you have an electron which is charged, but it's not moving, then it will feel no force inside the magnetic field. Okay? D'accord? Okay, now question B. Can a neutron undergo a Lorentz force? What would you say? Uh-huh. And how? If you compute this, it gives you what for a neutron? What's the charge of the neutron? Ah, the charge of the neutron is zero. Therefore, the Lorentz force on a Newton is also zero, okay? So these neutrons, we don't use them a lot at CERN because we cannot do much with them. They are not electrically charged, so we cannot accelerate them in an electric field. It doesn't work. An electric field only exerts a force on a charged particle, and we cannot modify their directions with the magnetic field because they don't feel the magnetic field. Okay? So neutrons, if you want to do physics with neutrons, you have generally a small nuclear reactor and you have these electrons coming out and you use tubes and you take them where you want. They don't move extremely fast. But you cannot change the direction or change their speed because you cannot do much with them. Okay, this is why at CERN you hear about protons, antiprotons. You can accelerate these in different directions inside the same rings. They do experiments with nuclei of gold, for instance. That's a few years ago they were doing that. A nucleus is something you can accelerate because it has a positive charge. You remove the electrons, so it's positive, you can accelerate it. But a particle that has no charge, you cannot accelerate it. Okay. Next one. What is the force undergone by a proton? A proton. Okay, let's have a proton here. Okay. If the magnetic field is perpendicular to the sheet, the magnetic field is perpendicular, its direction enters the sheet. Okay, so the magnetic field in this area is going down. Okay, I write a few of these vectors. Let's say there's a uniform magnetic field, and the proton goes from left to right. So the proton has a certain velocity from left to right. What do you think about the force is going to feel this proton? Hmm? This is the formula, okay? And this is now our situation. We have a velocity towards the right, and we have a magnetic field which is going downwards. Please don't be confused. This is seen from above, and this is seen from the side. Okay, so I'm doing the two drawings. Just don't confuse them, right? What would you say about the force? Do you remember the law? It's the same law. It's the right-hand law. Okay, but here what did we say? We say we should put the field in the direction of the middle finger. That's always the same. The speed of the charges in the direction of the index, and the force will be along the thumb for charges which are positive. Otherwise, for charges which are negative, the force will be in the opposite direction. Okay. Well, here we have a proton, so the charge of the proton is positive. So what do you say about the direction of the force here on this drawing first, maybe? Hmm? Hmm? Allô, allô? Take your right hand. Never use your left hand. Always your right hand. Be careful with that. Put your middle finger in the direction of the magnetic field. The magnetic field is going down. The velocity is to the right. Okay, and so the force is upwards in the direction of my thumb. Okay, so the force here is upwards. It's perpendicular to the magnetic field and perpendicular to the velocity. So what is this proton going to do inside this magnetic field? It's going to turn how? Yeah, it's going to turn like this. Okay, it's going to start doing circular motion as long as the proton is inside this constant magnetic field. I don't know until where it extends. It's going to turn that way, and it's going to actually move on a circle. Okay, if the magnetic field is wide enough, or if the velocity of the proton is slow enough, it's going to start making circles, right? And now if you look at it from here, you have the B which is going down, you have the velocity which is going to the left, and so the force now, it is going in like this, it's going down, but of course we see that from this side, okay, so it's correct. Right? And the last exercise is extremely easy, so I let you do it, because I want you to end up on a note of self-satisfaction. So let's imagine we have a magnetic field. Let's imagine we have a magnetic field which is uniform and which is going down like this. Okay, let's say we have a magnet here. Okay, here we have the north pole of the magnet, here we have the south pole, and between these two poles we have a uniform magnetic field. Okay, now we have a proton, and this proton is moving parallel to the magnetic field, so it's going down this way. What do you say about the force which is acting on the proton? What do you think? Well, again, write the formula. The Lorentz force is Q times V cross B. Okay? And maybe you remember what we said about the vector product. This is the vector product of B and V. This vector product is maximum when V is perpendicular to B. And it's zero when V is parallel to B. Okay? So if V is parallel to B, then V cross B is equal to zero. And so in that case, you have no force. Okay, the Lorentz force is again 0 newtons. So be a bit careful with the magnetic force. It's a force that is more complicated to comprehend than the electrostatic force or the gravitational force, because it does not depend only on the magnetic field, it depends on the direction of motion of the charges. Okay, so in this case, we had a uniform motion because the magnetic field was pointing downwards, and we have a large area with the magnetic field pointing downwards. And so the velocity of the proton is always in the plane, it's always perpendicular to the magnetic field, so the force keeps acting. But here, if you send this proton downwards inside the magnetic field which is going down, or even if the magnetic field was going up, it wouldn't change anything. In that case, there is no force acting. Are you amazed? Yes, I know. You are so amazed you cannot even speak. Okay? Do you have more questions about that? I will give you a real life example, because you guys, maybe you're never going to do physics, you're going to be lawyers. And if you're going to be lawyers, one day you will have a nice house. And in this nice house, you will have a garden. And inside your garden, you will have some electric tools to deal with the garden, etc. And you will have huge electric cables. Okay? And maybe you will have a 50-meter electric cable for your garden. So I tell you one thing, be careful and do the test if you want, okay? If you have an electric cable and you put it on the floor n'importe comment, this electric cable will have a certain resistance, which is fine, which is just that of 50 meters of copper wire. But if you take your electric cable, you roll it up nicely because you are an ordered guy, and then you use it on the other side to transmit current, you are going to have a lot of difficulty having current pass through this, okay? Because now you have all the loops from this wire which are next to each other, and there is an auto-induction, so there is a magnetic field which is created here. And actually, this magnetic field opposes the passage of the current. Okay, so you can try it with a long cable. You can try it even with a shorter cable. Okay, if you do that, you will have much less current passing in your cable because of auto-induction. This is something we didn't study, but it was to give you a bit of input on that. Okay. Yeah, just leave it randomly on the floor. Do not think that you're doing something good in electricity if you are making loops with cables. Avoid loops with cables when you do electricity, okay? Because there is an effect, there is a magnetic field of the cable, produced by the cable, but which acts on the cable itself. And this increases what we call the impedance of the cable. Impedance is a generalization of what we saw this year with this resistance. Electrical resistance is fine for resistors, okay? The little square things, they have always the same resistance. But now if you take a capacitor or a self, it's no longer the same way. The resistance of the self is not equal to the resistance of the cable that makes it. Okay? The resistance of the self depends on the frequency. If you have a low frequency, the resistance will be low. If you have a high frequency, the resistance will be high, up to a point where you can no longer have current passing through it, because if you change the current, then this is going to fight the change in the current. Whereas in a capacitor, well, if the frequency is low, the capacitor is not going to let anything pass. But if you have a current which oscillates very, very fast, then it's going to pass through the capacitor, because one of the plates is going to charge and influence the other plate, and vice versa when the current changes direction. Okay, so a self is actually what we call a high pass filter. It lets excuse me, I always confuse. It's a low pass filter. It lets all low frequencies pass easily, but not the high frequency. Whereas a capacitor is a high pass filter. It's going to let high frequency pass, but it's going to block low frequencies. And basically this is with these three elements, the capacitors, the selves, and the resistances, that we do all electronic, all analogy in electronics. And so these are the basis component of analogic electronics. And they work pretty much in accordance with the electric field for the capacitor and with the magnetic field for the self. Okay? Any other questions? Well, if it's not the case, then the course is finished. I got to the end. I did the last exercises. I did much more than the other years. I'm very, very happy. I hope you also benefited from that course online. At least some of you did. We will see next year, okay, how you do in the semestriel, which we do the first week. No, I'm joking. Maybe there will be teachers putting you a test after 2-3 weeks. We will see. We will see next year. Okay? Listen, I don't remember exactly everything I've read. Is it not the case that you are going to redo a test if you were insufficient only? You should ask a dean. I guess if you pass the year and your grade is okay based on first semester, you will keep that grade. I think it will be like that. But now let me not promise too many things, because I haven't read all the rules and details about the exams next year. I don't know. Okay? Okay, so have nice holidays and see you in the corridors next year, because you won't have physics any longer. Okay? Okay. Bye-bye. Bye. 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 Bye.